So in this example problem, or in this problem here, we're given a truss that's supported at 2 points. At point A, we have a pin, and at point G, we have a roller. All right, and we're asked for this truss to determine the force within members B, G, which goes from B to G. We have member BC and member HG. All right. All right. So if you're given a truss problem, if you're told explicitly to find three forces, or forces within only three members, that's usually a good hint that you should try to apply the method of sections. All right. All right. So the first step for the method of sections is you'll need to determine the reaction forces at the supports. All right. So in this case, we have two supports. We have a pin at A, and we have a roller at G. All right. So in order to evaluate or to find those reaction forces, we're first going to just draw a free body diagram of our truss. So if we do that, we'll have point A, we'll have AX, and we'll have AY. All right. Then we'll have the rest of our truss. We'll draw it all out. Right. At point G, we will have G of Y, and due to the roller, and then at point E, we'll have our applied force of 260 pounds. All right. We also should include any critical dimensions, so we can include the dimensions between of the members of the truss that's given to us. All right. And if you really want to go crazy, you can label all the points. All right. All right. All right. So once you have your free body diagram drawn, all right, you should then be able to apply the equilibrium equations to find AX, AY, and GY. All right. So the easiest one to do right away is we can sum all of our forces in the x direction and set those equal to 0. All right. So we have AX is going in the x direction, AY is going in the y direction, and GY is going in the y direction, so they'll have no x component. And then the 260-pound force will have an x component that will be proportional to, it'll be going along the negative x-axis. It'll be proportional to 5 over 13 times 260 pounds. All right. So if we rearrange this equation and solve for a of x, we get a of x will be equal to 100 pounds. All right, and it'll be going along the positive x-axis. Right. So the next force we can solve for, we can solve for a of y, and to solve for a of y, we can sum the moments about point G. All right, and set that equal to 0. All right, we should pick. You could also sum the moments about point A and solve for G of y. Both of those would be acceptable things to do. It doesn't matter which one you picked, but you should pick a joint or a point on the free body diagram where you have the most number of your applied forces going through that point. So point G, A of x goes through point G, G of y goes through point G. So the only two forces that we have to account for are the y component of the applied force and A of y. All right. So if we have A of y, if we use the right-hand rule, we'll create a clockwise moment about point G. So it would be, the moment would be, since it's clockwise, it would be a negative moment. So we could say it would be equal to A of y times 8 feet, because it's point A is 8 feet away from point G. And then for the applied force, we're only going to consider the vertical component of the applied force, which is going in the negative y direction. And again, if we use the right-hand rule, that would cause a negative moment or a clockwise moment about point G. All right, so it's again going to be negative. So the y component of the 260 Newton for 260 pound force. All right, times the length between point G and point E. So that's going to be 8 feet as well. All right, so if we rearrange this equation to solve for a of y, what we'll get is a of y is going to be equal to negative 240 pounds times 8 feet divided by 8 feet. All right, so our 8 feet will cancel out and we'll just get minus 240 pounds. All right, so we're left with our only unknown in this situation is g of y. So if we sum all our forces in the y direction and set that equal to 0, all right, we'll just be left with uh, g of y plus a of y, which we just solved for, is equal to minus 240 pounds, and then plus the y component of the 260 pound force, which would be equal to minus 12 over 13 times 260 pounds. All right, so we'd end up getting, if we rearrange this equation, what we end up getting is we would get g of y. Oops. So if we moved all the negative forces to the other side, we would get g of y is equal to 240 pounds plus 240 pounds, which is just equal to 480 pounds. All right, so now the first step of our problem is finished. We determine the reactions at our two supports. All right, so step 1, all done. All right, so step 2, we're going to take our section cut. So we're going to take, so for step 2, what we're going to do is we're going to take a section cut through our members of interest. All right, so our members of interest are going to be our BC, BG, and HG from the problem statement. So if we draw our truss, right? So we'll draw our truss at point A. We'll have A of X, which was equal to 100 pounds. We'll have A of Y, which we'll now draw going along the negative Y direction, and that would be equal to 240 pounds. All right, and then we have at point B and point H, we'll have our members there, and then we'll draw our members that go from point B to point C, from point B to point G, and from point H to point G. We'll draw them with some dotted lines here. And then we'll include the right-hand side of our truss. We'll draw just like we did the left-hand side of our truss. All right, and we'll make sure to include our external force of 260 pounds and our reaction at G of 480 pounds. All right. So, make sure to include our important dimensions in our diagram, and then when we take our section cut through our truss, what it's going to leave us with is we're going to have some internal forces that will be exposed. So we'll have our force within B from point B to point C. We'll have our force from point B to point G, and we'll have our force from point H to point G. Right? And then on the right-hand side of our section cut AA, we would have equal and opposite forces. So we have the force that would go from point C to point B, the force that would go from point G to point B, and the force that would go from point G to point H. All right? So FBC is equal and opposite of FCB. FBG is equal and opposite of FGB. FHG is equal and opposite of FHG. So if you added the internal forces together, you would get no net force, and we'd end up with our original truss. Okay, so with this method, we can look at the left-hand side of our section cut, and we can look at the right-hand side of our section cut. All right, and then you can use either side. So either side is fine. To use to find our unknowns. In this example, we're going to use the left-hand side. The reason we're using the left-hand side is that it's a little bit simpler because it only has two force components, AX and AY, while the right-hand side has three force components. It has it has G of Y, it has the applied forces X component, and it has the applied forces Y component. Right? So that's why we're using the left-hand side, but you could totally use the right-hand side. You'd get the same exact answer. Right? So now I'm going to just redraw the free body diagram of the left-hand side. Of our section cut. All right. So we're going to include our internal forces. All right. So FBG goes along a 3, 4, 5 triangle. All right. And then FCB, if we look at the original truss, it goes along a triangle that has a 4 meter. It goes 4 meters in the X direction. It has 1 meter in the Y direction. All right. All right. So to solve this problem, we can use we can use our equilibrium equations. So when you're doing these types of problems, it helps if you can take the moment about a point where two of the known forces intersect. So in that case, what you could do is you could sum all of our sum the moment about point B. All right, for our left-hand side. So the main assumption of this method of sections is that this section of the truss must be in equilibrium. So we can say that the sum of the moments about point B must be equal to 0 in order for the truss to be in equilibrium. Therefore, we can say that the moments about B would be equal to A of X times 3 meters plus A of Y times 4 meters, and then plus FHG times 3 meters. All right, this is 4 meters here, this is 3 meters here. So that's where the moment arms are coming from here. And then if we solve for FHG, we get FHG would be equal to negative AX times 3 meters plus AY times 4 meters divided by 3 meters. So we would get FHG would be equal to minus 100 pounds minus 320 pounds, which is equal to minus 420 pounds. All right, if you plugged in AX and AY. All right, so again, to determine whether or not your moments should be positive or negative, remember you should use the right-hand rule. All right, that one should help you determine whether or not what direction your moment should be in. Okay, so to determine FBG and FBC, what we're going to do is we're going to sum the forces about the x and the y direction. All right, so it use sigma sum of forces x is equal to 0, and the sum of the forces in y direction is equal to 0 to determine FBC and FBG. All right, so we're first going to use the sum of the forces in the y direction because there's less forces. So if you do sum of all the forces in the y direction and set that equal to 0, we should end up with minus 240 pounds, that's from A of y, plus FBC times the sine of the angle, I'll call this angle theta, right, where theta would be equal to the inverse tangent of 1 meter over 4 meters, all right, and then FBG would have a negative 3/5 component along the y direction. All right. So what we're going to do here is we're going to rearrange this equation to solve for in terms of FBG. All right. So if we rearrange this equation for FBG, FBG would be equal to 5/3 FBC sine theta minus what is that? Minus 5/3 times 240 pounds. Right? Then we can sum our forces in the x direction. All right. In that case, we would get 100 pounds plus minus 420 pounds, which is due to FHG. All right. Then we'd have the x component of FBG, which would be equal to whatchamacallit here, FBG would be equal to 4/5 times FBG plus FBC times the cosine of theta, where theta is the same theta as we defined earlier. Okay, so again, we can plug. What we're going to do now is we're going to plug in this part into equation FBG, so we only have everything in terms of FBC. So if we do that, what we'll end up getting is we'll get 320 pounds from combining these two forces on the left-hand side of our equation. And on the right-hand side of the equation, we'll get 4/5 times minus 240 pounds plus FBC. Sorry, I made a mistake. Let's go back here. So we get minus 5/3 times 240 pounds plus 5/3 times FBC sine theta. All right, and then we end up with plus FBC cosine theta. All right, since we know what sine theta is and cosine theta is, since we can determine theta, what we can do is if you evaluate this whole bunch of equations, what you'll end up getting is you'll get 640 pounds is going to be equal to 1.2935 times FBC. All right. Once you have that, you can then solve for FBC. Right, FBC would be equal to 494.77 pounds. All right, you could plug FBC into the equation for FBG. All right, which is, I'll highlight in yellow here. All right. So you plug that in. All right, if you did that, what you end up getting for FBG is you'd end up getting minus 200.00 pounds. All right, and then so in summary, we were able to solve for our three forces: FHG, FBC, and FBG. All right. So FHG was equal to 420 pounds. All right. When we solved that problem, we found that it was actually had a negative magnitude, so therefore it must be in compression, based off of the free body diagram. So FBC we found to be a positive magnitude, so it was equal to 425 pounds in tension. All right, and then the last thing was we had FBG was equal to 200 pounds in compression. All right, so those are our three values, and that's how you can apply the method of joint sections to solve for the force within any three members of a truss.